All right, our next speaker is going to be Changwoo Min. He's a postdoc at Georgia Tech working in the lab of Taesoo Kim, and he's going to be speaking to us about a fascinating approach to finding bugs in code by comparing different code bases that are written to the same API. And he will be on the job market as well, interested in academia and industrial research lab jobs next fall.
Thank you for the kind introduction. Hello everyone, I'm Changwoo Min. I'm from Georgia Tech. This talk is about how to find the semantic bugs in file systems by comparing multiple file system implementations. This is a joint talk with my colleague Sanidhya Kashyap, Byoungyoung, Chengyu, and my advisor, Professor Taesoo Kim. Today, software is too large to be bug-free. In order to help to make the software a bug-free software, there are two promising approaches. The first approach is formal proof. Formal proof guarantees high-level invariant, such as functional correctness. For example, this high-level invariant is a functional correctness of software which is certified by the formal proof method, guarantees its correctness. The second approach is model checking. Model checking can find the violation of model in existing software. If model is a locking rule, model checking can find the locking rule violation in the existing software. But the precondition of using these two technology is software developer should provide proof or model. But unfortunately, many softwares are already written without such theory. One of the interesting things is there are many existing software that exist which provide very similar or almost the same high-level semantics. For example, we have more than 50 file systems in the Linux, and of course, all of the Linux file systems provide the Linux file system semantics. And there are also a bunch of JavaScript engines which all support ECMAScript specification. So, a motivating question of this research is, without providing proof or model, can you leverage existing multiple software implementations to help to find bug? In this work, we will focus on the file system bug. The reason that we are focusing on the file system bug is file system bugs are really critical. And we have been found, our community have been found a file system bug, a very critical file system bug in every year, even in case of the very mature file systems such as ext3, xfs, and ext4 as well. One of the reasons such a very critical file system bugs are still exist in very mature file system is majority of the file system bugs are really difficult to find. In fact, almost 90% of file system bugs are semantic bugs. In this talk, semantic bugs means logic bug. So without understanding the surrounding logic, it is very difficult to find such bug and correct such bug. So we'll focus on semantic bug in this work. Let me give you a real example of the semantic bug in the file system. This is one of the semantic bug, missing capability check bug in widely used distributed file system in OCFS2. And by adding these two lines of the code, we can simply fix this code. But without understanding the context of the OCFS2 extended attribute operation, it is very difficult to find this bug. So our question is, can you find this bug by leveraging existing other file system implementations without providing proof or model? Okay, let's check how other file systems implement the same functionality. And majority of the file system already correctly implement the same functionality, and they all have the proper capability check. So if that is the case, can we consider the deviant implementation, in this case the OCFS2, as a potential bug? Actually, this is the key intuition of our approach in finding bugs. And this is one of the bugs that we found in this work, and this seemingly very simple bug has been hidden for 6 years. And let me give you another more interesting and more complicated example, writing a page. Each file system should define how to write a page because they can define their own disk layout. And Linux documentation specifies the rocking rule of the write page operation. And a successful return, a page should be rocked, and in case of the error return, page should be unrocked. So our question is, can you find this kind of bug by leveraging the multiple file system implementation? In other words, if majority of the file system already correctly follow the rocking rule, can you consider one or two deviant implementation as a potential bug? In fact, based on this intuition, we can reveal such bug without domain-specific knowledge. We compared 54 Linux file systems, and we found 3 bugs in 2 file systems. And all of the 3 bugs has been hidden for more than 5 years. From these 2 examples, common observation is bugs are rare, and majority of the implementation is correct. So our approach in finding bugs is comparing multiple file system implementations to find the deviant ones as a potential bug. In this work, we explored this idea into the Linux file system domain, and we got very promising results. We found 118 new semantic bugs in 54 Linux file systems, and majority of the bugs we found are really critical. They can cause system crash, user data corruption, and can cause a system dead run. And many of the bugs are difficult to find, so the bugs were hidden for over 6 years on average. And based on this intuition, we could find various types of the semantic bug, including incorrect condition check, and incorrect argument usage, and incorrect return value handling, and rocking rule violation. The idea of comparing multiple software implementation to find the deviation sounds quite straightforward, but designing and implementing such idea is really difficult. The key reason is even software provide the same or similar high-level semantics, all software are different in nature. For example, even all Linux file systems provide the same Linux file system semantics. They can adopt the different disk layout, so all Linux file systems are different in nature. So key technical challenge here is how to compare different software implementation. In order to tackle this technical challenge, we should answer 3 questions. The first question is where to start to compare. The second question is what to compare, and the final question is how to compare. In this work, we design and implement such a system named Juxta, which compare the multiple file systems to find the potential bug. This is the architecture of the Juxta. Juxta first performs the symbolic execution for Linux file system source code, and then create a path database, which is composed of the execution path information. And Juxta also provides 2 statistical path comparison mechanism. And then based on these 2 mechanisms, the path comparison and the path database, we developed 7 checkers. Each of our checkers are targeting for specific types of the semantic bug. In this talk, I will mainly explain our path condition checker and argument checker. In the rest of the talk, I will explain how Juxta compare multiple file system implementation. Let me first start by answering the first question, where to start to compare. For the comparison, we should start to compare the semantically identical entry point. In the Linux, such a semantically identical entry point is VFS entry point. VFS can be considered as an abstract-based class of all Linux file systems. It defines the common data structure, such as inode, and it also defines the common behavior, such as accessing the page cache. And it also calls the file system specific implementations through predefined interfaces. And inode operation is one of such example. So for a file system wants to provide a rename operation, it has to implement its own implementation of the rename, and then provide its interface through the inode operation interface. So regardless of file system, the file system specific rename implementation should have the same high-level semantics. So when we say the Juxta will compare rename, what actually Juxta compare is the file system specific implementation of rename. We call these functions as the VFS entry point. Now we decide to start to compare from the VFS entry point. And next thing is what actually we have to compare in the VFS function. We decide to compare the result of the symbolic execution. The reason that we decide the symbolic execution result is our symbolic execution is context sensitive and flow sensitive. So the result of the symbolic execution can have more rich information, can represent more rich behavior of function. So while executing the symbolic execution, we collect path condition, return values, side effect, and function calls. The key idea of our symbolic execution is return-oriented comparison. For example, if we compare the all execution paths returning the permission error in rename function, we can further constrain the high-level semantics of the rename. Let me show you how our symbolic execution engine collects the execution information. It starts from the function entry point, and then let's suppose that our symbolic execution engine decides not to take this if branch. We can collect the path condition as a flag is not read-only. Then by executing the subsequent program sentences, we can collect the side effect and global function calls. When symbolic execution engine reaches to the return statement, our symbolic execution engine aggregates all the collected information from the function entry point to the return value. And such a collected information is aggregated into our past database. In this work, we analyzed 54 Linux file systems, which is composed of 680,000 lines of code. And it has more than 8 million execution paths, and its size is more than 300 gigabytes. Now we create the past database, which is composed of the past information. And now it's time to answer how to compare these collected past information. If you look into the past information in more detail, there are two types of the data. The first type is the range data. The process of the symbolic execution is the process of building symbolic constraint. And symbolic constraint can be represented as a numerical range data. So in this work, the past condition and return value can be represented as a numerical range data. The second type of the data is event occurrence. For example, how many times a particular API flag is used? This kind of question can be modeled as an event occurrence. In this work, API argument uses and the pattern of the error handling can be modeled as event occurrence. Juxta provides a different statistical comparison method for different data type. And for the range data, we propose the histogram-based comparison. The purpose of the histogram-based comparison is to compare range data and find deviant sub-ranges. Histogram-based comparison is composed of the three steps. We first represent the range data into the histogram. This process is quite straightforward. Please see the details in our paper. The second step is build a representative histogram by using histogram average operation. As I said before, the purpose of the histogram-based comparison is to find deviant sub-ranges. In order to find the deviant sub-range, we need to define what is the majority. And the histogram average operation is one of the ways to represent the majority. And the third step is calculate the distance between the average histogram and the per file system histogram. Each last step is for finding a deviation. Let me explain the histogram-based comparison in more detail by explaining our past condition checker. Let's suppose that we have a three file system, foo, ba, and cat, and we will compare the permission error case of the rename function. And as you can see in this figure, there is an error in the cat file system because its flag comparison is wrong. And we first represent the range data into the histogram. And I'd like to mention one thing in here. our histogram representation preserve the range information. And then build a representative histogram by performing the histogram average operation. In this example, histogram average operation is simply add the histogram of the 3 file systems and then divide by 3. This simple histogram average operation have a nice property, such as it maintains the commonly used data range, such as in this case the flag comparison with read-only maintains high in magnitude, and rarely used sub-data ranges, such as in this case the flag comparison with write-only decreases in magnitude. Then we calculate the distance between file system histogram, full histogram, and average histogram, VFS histogram. And the histogram distance is calculated by measuring the size of non-overlapping regions. We calculate the histogram distance for all 3 file systems, and as we expected, the distance of the CAD file system is the largest because the size of the non-overlapping region between the VFS histogram and CAD file system histogram is the largest. Then our path condition checker rank a report based on the distance. Since larger distance means there is a more deviation from the average histogram, we can consider larger distance means more deviant. And also, by analyzing the non-overlapping region, we can also report what is the missing condition check and what is the unique condition check in here. Using this histogram-based comparison, we found 59 new file system bugs. The second type of the data in path information is event occurrence. And in order to find the deviant event, we propose event-based comparison. In our system, function argument usage and pattern of the return value handling can be modeled as an event occurrence. For the entropy, we use the classical Shannon entropy function. Let's suppose that we have 2 types of event A and B, and this graph is a classical Shannon entropy graph, and x-axis represents the ratio between the 2 events, and y-axis represents the entropy value. If only either of one event occurs, entropy value will be 0, the minimum, and if both of the events completely randomly occurs, so its event occurrence is the same, the entropy value will be the maximum. In terms of the finding deviation, the sweet spot where we have interested in is the case with small entropy values. For example, while event A occurs 98 times, event B occurs only 2 times, we can consider event B as a deviant event. Our argument checker rely on event entropy-based comparison. Our argument checker can statically identify incorrect use of API flag in file system without any special knowledge. In this talk, I will use the case of the KMellow, which is the kernel memory allocation API. Unlike the user space memory allocation API, developers should provide additional argument which describe how memory allocation requests should be served. Under the subtle context of the file system developers should use GFF NoFS argument to avoid the deadlock. Our argument checker first count the KMellow flag uses for each VFS entry functions and then calculate the entropy. As you can see in this example, there is 2 deviant KMellow argument uses in the file write operation. So its entropy value is the smallest. Then our argument checker rank the report based on the entropy. So in this case, smaller entropy means more deviant. Using this entropy-based comparison, we found another 59 new file system semantic bugs. Until now, I explained how Juxta create the path database and how Juxta compare the collected path information using statistical path comparison method. Based on this, we developed the 7 checkers which targets the specific types of the semantic bugs. We implementation of Juxta is composed of the 12,000 lines of code, and for the symbolic execution, we extend the Clang static analyzer. For the statistical comparison and the checkers, we use the Python as for other developers easily extend their own checkers and the comparison mechanism. We apply the Juxta to the Linux kernel 4.rc2. For the evaluation, we have 4 questions. The first question is how Juxta is effective to finding new semantic bugs. The second question is what types of semantic bugs can Juxta find? And third question is Juxta's completeness. And the last question is how effective is Juxta in ranking scheme? We apply the Juxta to 54 Linux file systems, which is composed of 680,000 lines of code. And our 7 checkers generated 2,382 bug reports. Among these bug reports, we manually verified highly ranked 710 bug reports. Then finally, we found 118 new bugs. This result shows that Juxta is very effective at finding new semantic bugs. And as I said before, each of our checkers is targeting specific types of the semantic bugs. And fortunately, all of our checkers succeeded in finding at least 2 or more semantic bugs. So Juxta can find various types of the semantic bugs. In order to test the Juxta's completeness, we synthesized 21 known file system bugs into our testing kernel to see Juxta can find all of them or not. In fact, Juxta found 19 out of 21 bugs. And Juxta missed the 2 bugs because of the incompleteness of our symbolic execution. For Juxta to be practical, developers' effort to investigate Juxta's bug report should be minimal. This graph shows the Juxta's ranking scheme is effective to save developers' effort. In this graph, x-axis represents entropy-based ranking. So the leftmost part represents the highest ranked bug report, and rightmost part represents lowest ranked bug report among the verified ones. And y-axis represents the cumulative number of new bugs that we found. And as you can see in this graph, we found most of the bugs from the highly ranked bug report. In fact, more than half of the real bugs that we found from the top 100 bug report. Juxta is good, we think, but it has its own limitations. One of the key assumptions of the Juxta is deviation will be bug, but deviations do not always mean bug. That is one of the source of the incorrect Juxta's bug report. And in order to apply the Juxta, we need at least 3 implementations. And finally, as you see in the previous slide, Juxta's symbolic execution is not complete because of well-known state explosion problem and the limited interprocedural analysis. Despite of this limitation, we think Juxta's approach is very promising. And we have many promising directions for further research. One of the such kind of direction is self-regression tool by handling the subsequent versions of the same software as a different software implementations. And the second one is cross-layer refactoring tool. If you may remember my first example, the capability check, you may wonder if all file system needs a capability check for the specific API, such capability check should be in the upper layer. Actually, we found many of such cases while investigating our bug reports, so we think Juxta can be naturally extended to the cross-layer refactoring tool. And we think there are many important and interesting set of software that Juxta can be easily applied, including the device drivers and JavaScript engines. To conclude, in this work, we tested the approach of comparing the multiple software implementations to help to find the bug. And we built a tool named Juxta to find the bugs in the file systems. We will open all of our source code and databases soon. This is the end of my talk. Thank you very much. I will take your questions.
Jajasai, Sony Brook University. Very interesting idea. So it seems like why Juxta could be so helpful is because you have 54 system call, file system implementation. So, but for other system, might not be so lucky. So you might have only 2 or 3 implementation actually. So exactly how many implementation do you need to make it like have sensitive result? Like from your experience?
Well, we have no very concrete answer for now because we only adopted this approach in the case of the file system. But I think the minimum number of implementation to apply the Juxta will be definitely more than 3.
More than 3. Okay. Thank you.
Jeff Canning, Harvey Mudd College. So sort of following up on that. Back in 2001, Dawson Engler did something very similar to this, where he went through the Linux kernel, and what he was looking for was sections of code that were similar to each other, and from those he inferred assumptions and then found bugs where those assumptions were violated. So could you comment on the differences between your approach and Dawson's approach?
Actually, Juxta's approach can be considered as an extension of Dawson Engler's idea. And our focus is how to compare the totally different software implementations, but they provide the similar high-level semantics.
Thank you.
Ryan Huang from UCSD. You mentioned that you need to manually verify these reports. So, and it seems like there are a large number of reports you need to verify. So, quantitatively, how much effort you need to spend on like verifying a report?
Comparing to the other, for example, bug finding tool, the purpose of the Juxta is to finding the semantic bugs. So investigating the bug reports seems to take a little bit longer. In this work, we analyzed the 710 bug report by the 2 of our authors for 2 weeks.